worth of view. Really, all this is a circle with a point rotating around the circle. But see its projection in the x and the y direction. And if you kind of follow the up and down or the sideways motion, they're not uniform. They speed up towards the center, and as they get to the end, they slow down and then reverse. Another little animation I've got here. So I think this works. No, that's not it. Wrong point. It's the point we want to animate, I think. That's the right idea, but it's still not what I wanted. Try again. There we go. So again, you just have a point going around a circle with a line attached to it. And another point just kind of tracing its behavior. And before I go on, I have like a, stop this. I have a little video, it's like a 30-second video or so, something like that. No, 1 minute. Just on kind of the same subject.
What a bright spot moves around the circle. What you actually see depends on your point of view. You see a true circle only if you look at it in the right direction. You might see motion along an oval curve called the ellipse. Or you might perceive the motion as being straight up and down, as though the spot was casting a shadow. The height of the shadow above or below the shadow axis can be measured on a vertical y-axis. When you plot y against the angle t, you get a graph called a sine curve. The number y is called the sine of t. This way, y equals sine t.
Let's see. So, I think the connection you want to remember between these animations and what we were doing previously is that our new, more comprehensive definition of sine and cosine curves, or functions, is that we have some angle which is now directed in the counterclockwise direction. And we have this point on the unit circle, and the coordinates of this point are cosine of theta and sine of theta. That's why when you kind of extend the line out and you move a point outward, as this is going around the circle, you get that sine curve. And of course, you get a similar curve if you were looking at the x-coordinate. We don't call that a, well, you could call it a cosine curve, but in general, we just call those curves sinusoids or sine curves. I want to go over something again that some of you, I'm sure this is like just a review, but it's so important. It's going to be important. So I want to make sure everybody's on the same page. Has to do with these two important triangles. Well, really 30, 60, 90 triangle, and an isosceles right triangle, 35, 45, 90. Just want to review the fact that with some very, very little basics in geometry, you can figure out the sines and cosines of a number of important angles. So the first one I want to review is we start with an equilateral triangle, one whose angles are all the same. So therefore, they must be what? It must be 60, yes. And I drop an altitude. Altitude is a line from one vertex to the other side that meets at a right angle. And then recalling from geometry some congruence theorems, we know these sides are congruent because it's an equilateral triangle. If we're looking at this triangle and this triangle, we know this side is congruent in both triangles because it's the same side. And we know they both have a right angle here. So we use the congruence theorem, hypotenuse leg, to say these two triangles are equal. And that gives us the important result that I'm looking for, which is these two sides and these two angles must be congruent. Well, if these two are equal, and they're equal, you know, their length is equivalent to one of these other sides, then if I give this a value, say this side has a length of 1, this has to be half. And if I know the hypotenuse in one of the legs, I can use the Pythagorean theorem, which tells me that let's call this x for the moment. We know x squared plus a half squared equals 1 squared. Right? A squared plus b squared equals c squared. And so if we solve for x, what are we going to get? X squared is going to be just 1/4. 1 minus 1/4 is 3/4. Or x will be the square root of 3 over the square root of 4, which is 2. So x, this side, is going to be the square root of 3 over 2. I go over that whole thing because it's something you should be able to do yourself in a pinch if you're trying to figure out the sines and cosines that we're about to show, you can do it if you remember this process. So, okay, well, what does that have to do with geometry? We want to know what the sines and cosines of 60 and 30 degrees are. So let's start with the sine of 60 degrees. Well, we know the sine is the opposite over the hypotenuse. So right away I have an exact value for the sine of 60 degrees. Cosine of 60 degrees is just going to be the adjacent over the hypotenuse. So again, you immediately know that's exactly 1/2. And if we want to just throw in the tangent here, the tangent is the sine over the cosine. It's the square root of 3 over 2 over 1/2. Then dividing by a fraction is multiplying by its reciprocal, so this is just square root of 3 over 2 times 2 over 1 is just square root of 3. Okay, so much for 60 degrees. 30 degrees is the complementary angle, and we know that the sines and the cosines will reverse. So we know immediately that the sine of 30 degrees is going to equal 1/2. Cosine of 30 degrees equals square root of 3 over 2. And the tangent of 30 degrees, well, it's just going to be the reciprocal of this. It's just going to be 1 over the square root of 3. To know these one way or another. You either need to be able to figure them out. If you want to just memorize them, that's possible, although I find when you try and memorize just some kind of random data like this without context, it's easy to mix things up. Which is the sine and which is the cosine and so forth. Okay, that's 30, 60, 90 gives us 30 degrees and 60 degrees. That's, I guess it's these two triangles I'm thinking of. For the isosceles right triangle, it's a lot easier. We know since two sides are equal, the angles have to be equal, and therefore they have to be 45 degrees. If we just assign some value to one of the legs, say 1, we can again use the Pythagorean theorem. We'll know 1 squared plus 1 squared is the hypotenuse squared. So the hypotenuse is just going to be the square root of 2. And from this we can derive the sines and cosines pretty easily. The sine of 45 degrees will of course be what? 1 over the square root of 2. The cosine, of course, will also be 1 over the square root of 2. The tangent, 45 degrees, which is the sine over the cosine, will just be 1. So again, it's something you should either know, like right off the top of your head, or be able to derive it. I often find if you know how to derive it, it kind of sinks in and you don't really have to. Okay. Any questions about this? I assume this is hopefully in review for most of you. The next thing I want to do is I want to take this information and apply it over here to my idea of my circular definition of the sines and cosines. specifically, I want to see what all the possible angles I can learn from these, as well as the intersection points. I'd like to find out what all of them are. So I think I'm gonna go around the room and, you know, I think this should be okay. If you're a little flustered, don't worry, just pass. But let's start in the back. We'll start with Ian. We'll move our way around. I guess it would be nice if I left these up. 3, and draw my circle here. And I'm just going to start here with 30 degrees. And I want to find the cosine and the sine of that. So, Ian, what would the cosine of 30 degrees be? Looking for an exact value.
On the board, the square root of 3 over 10.
Yes, you don't have to be embarrassed by the obviousness of the answer. Stephen?
For sine would be 1/2.
Sine would be 1/2. Okay. So now we're going to move a little further to 45 degrees. And who's next? All right. What would the cosine of 45 degrees be?
Would that be root 2 over 2? Root 2 over 2.
Okay. Some people like to rationalize the denominator. I don't care, but that's fine. Okay, and then my brain is not working. Harold.
Would it be like 3/4 or something? No.
Looking for the, this was the cosine, so looking for the sine of 45 degrees. And it's on the
Oh,
board.
just kidding. What is square root of 2?
It's not the square root of 2.
1 over square root of 2.
1 over the square root of 2. These are the same, by the way. I'm writing them differently. It's just you rationalize the denominator. Okay, 60 degrees. Paul. The cosine of 60 degrees.
1/2.
1/2. And Christina, the sine of 60 degrees.
Square root of 3 over 2.
Square root of 3 over 2. Okay, so far that's been pretty easy, right? Just look on the board and kind of fill in. Here we go. The cosine of, this is now 90 degrees. We didn't talk about this, but recalling that the cosine and the sine are just the coordinates of this point.
Is it 0?
Cosine of 90 degrees would be 0. And Luis, the sine of 90 degrees, and it's just the coordinates of this point. 1. Okay. We've done the easy stuff. Doesn't get real hard. The next angle is this angle. It's 90 plus 30. This is 120. And I want to point out that its reference angle, remember reference angles? Its reference angle, reference of 120 degrees, is going to be 180 minus 120, or 60 degrees. So all you really need to know to figure out the sine and cosine of this angle is to look at the sine and cosine of this angle and then figure out how the SIGN changes. Remember, sine and cosine here are positive and positive. The sine and cosine, since the coordinates down here are minus, minus, they have to be minus, minus. Coordinates here are minus, plus, and the coordinates here are plus, minus. So now we want the cosine of 120 degrees. So who's next? Are you up next, Albert? You're next. Yeah.
Is it negative a half?
Negative a half. Does everyone see why that is? It's the same as this point, 1/2, but now cosines are negative. Okay. Ashley.
Positive.
Square root of 3 over 2. Okay, good. All right. Now we're over to 135. 90 plus 45. So again, the reference angle, 135 minus, 180 minus 135 is 45. So the cosine of this angle is did I skip? No, I haven't skipped anybody. Yes. So the cosine, recall, this is now the reference angle. So all we have to do is figure out the sine.
It's negative. Bracket 2 over 3.
Sure. I'm just going to write this as 1 over the square root of 2, but you're welcome to write the square root of 2 over 2. Okay, Heather? The sine must be
1 over 42.
all right. Moving along now. This angle is 150 degrees. So its reference angle is 30 degrees. So we can just look at 30 degrees here. Jada?
The cosine?
Cosine of 150 degrees.
Negative square root of 3 over 2.
Okay. Henry?
Sine is 1/2.
Okay. And Carlos, we did, again, this is one of the intersection points.
Negative 1.
Okay, so the cosine of 180 degrees, that's what this is, negative 1. And Kayla?
0.
0, okay. So we didn't really write this in, I'll do this. This is 1, 0. So the sign goes from 0 up to 1 and then back to 0. Now it's going to go negative, right? Okay, move 30 degrees further, that's 210. But now, when we figure out the reference angle, it's not 180 minus 210, it's 210 minus 180. It's 30 degrees. Again, we can look at our reference angle, but
So negative square root of 3 over 2.
negative square root of 3 over 2, and 1, the sine of 210 is okay. Oh, I don't want to leave you out. Okay, so now we have 180 plus 45, that's 225, minus 180 is 45. Okay, so that's, now our reference angle is 45. What's the sine? You could do both. What's the sine and cosine here? Yeah? Negative square root of 2 over 2. All right. We'll go a little further, but I hope everyone's getting the idea here. It's not all that hard, right? You just need to know, really there's 3 values other than 0 and 1, right? And if you know where they are over here, and you know how the sines and cosines change their SIGN as they go around, you've got it made, right? You've got the whole circle. I'm not gonna go through all the cosines and sines, but I just want you to hear. Here we have 180 plus 60, so that's 240 degrees. Here we have at the bottom 270. 30 degrees further will be 300 degrees. These are all angles that we can get the exact sine and cosine of. 270 plus 45 is 314. And then finally 330 degrees. You can also, you can get to these another way. This is minus 30 degrees, right? This is minus 45 degrees, minus 60 degrees, minus 90 degrees, right? Okay, you want to take a picture, take it now. You need to know all this, right? It's real basic. If you get a problem and the problem says, well, what's the cosine of 315? You have to have some idea how to construct that, how to get to that. You should be able to do that. Okay. Okay, it's okay if I erase all this now? Oh, something I didn't, I mentioned that in the first quarter, the reference angle is just the angle, right? Second quarter, reference angle is 180 minus the angle. In third quarter, reference angle is 180 plus the angle. And then what's the reference angle in the fourth quarter? To be consistent, I should give you a positive value, but I kind of like the idea that it's just the negative of it. That is, the reference angle for negative 30 is just positive 30. You can just look at this point to find out this guy's sines and cosines. It's just his cosine will be negative. But to be consistent, to make this positive, I have to say add 360, so it's 360 minus the angle. Okay. All right. Okay.
Oh, yeah.
We're going to do something with these in a minute, but do we do? I'd like to remind everyone, I think most of you will be familiar with this. We have, for an angle, we have the sine and the cosine. And these two are, we found they are related in some way that we'll see later. I mean, they're graphs. Look. They kind of look like it's the same function, just kind of shifted, and we'll hammer that down a little. But now we have another function we call the tangent theta, which, depending upon whose approach you take, you can define it as opposite over adjacent. You could also define it as the sine over the cosine. This works a little better in our circular environment because we're just dealing with triangles, then we don't really know about angles beyond 90 degrees. There are three other functions that we're going to define. One of them is the cotangent. I'm going to first write out cotangent. Its abbreviation could either be COT theta or CTN of theta. See both of them used. And these are defined as 1 over the tangent. They're just its reciprocal.
Is that like the inverse of the tangent? Cotangent?
It's not the inverse, it's the reciprocal. Let's be very careful here. I could write this way. To the -1, that would be reciprocal. We want to be very careful because there's something else. We're going to use this terminology, tangent -1 theta, not to mean this, not to mean the reciprocal, but to mean the inverse function. We'll get to that later. The same is true of sine and cosine. And any of you who have a TI or any other calculator, if you look at it right now, you will see that this is a button, right? They don't mean the cotangent. They mean the inverse tangent. Most calculators won't have a cotangent function key. They just expect you to know, since you can do a reciprocal real easily on your calculator, that that's how you're going to get this. Okay. And then we have these two other functions, the secant, which we write SEC, SEC of theta, which is defined as 1 over the cosine of theta. And the cosecant, so I'm going to write this out, the cosecant, which is abbreviated CSC of theta, which is 1 over the sine of theta. Okay, so we've got the tangent and the cotangent are reciprocals. The cosine and the secant are reciprocals. And the sine and the cosecant are reciprocals. It's worth pointing out from a memorization point of view, that mathematicians were not kind when they gave these things their names. It would have been so much more straightforward if the reciprocal of the sine was the secant and the reciprocal of the cosine was the cosecant. It would have been so much easier to remember. Now you have to remember not just that they're reciprocals, but that the co here goes with the not co, and the not co here goes with the co. Like it does with the tangent. Sorry. Can't fix that. All right, so we're going to look at these a little bit. But first, I thought it would be nice to do just some simple practical problems with trigonometry. So you get a feel for how we can use these functions. Let's start with a very simple problem. I probably could do this just geometrically, but I'm not. I'm going to use my trig functions. So I have a triangle. It's a right triangle. I know that the hypotenuse of that triangle is 12, and I know this angle is 30 degrees, and I want to solve the triangle. That is to say, I want to find all the other parts. So the first part is very easy, since some of the angles has to be 90. I know that this angle is 60 degrees. Now I want to find the opposite side and the adjacent side. I know that the opposite over the hypotenuse is going to be the sine of what angle? 30. And I know the hypotenuse, so I can rewrite this as O equals H sine 30 degrees. My H is, of course, 12. So now I just need to recall what the sine of 30 degrees is. Well, it's in the first quadrant, so it's positive. The choices are square root of 3 over 2 and 1/2. Anyone recall which of these it is? It's 1/2, yeah. 12 times 1/2. So this side here is just going to be 6. Similarly, the adjacent over the hypotenuse is going to be the cosine of 30 degrees. So I know the adjacent is going to be 12 times cosine of 30. And it's not a big guess at this point. 30 degrees has to be square root of 3 over 2. So this is now 6 square root of 3. Okay. It was a pretty simple problem. We could have used geometry, but that's not always going to be the case. Let's try something that would actually be practical. So I'm walking through the woods because it's my job, I guess, and I see a very tall tree. And I want to know how tall that tree is. So I measure out from the base 532 feet. And I have a little, kind of called a sextant, And I measure from the ground to the top, I measure an angle of 25.7 degrees. Oh. is a little different from this because I don't know the hypotenuse. I might want to find that out too, but really what I want to know is how tall is this tree? That's my x. Okay. So what's a trigonometric relation I could create using this angle, this known distance, and the unknown x? Everyone had some time to think about this? One of my trig relationships, it tells me something about the two legs, right? I guess this is, we call this the opposite, we call that the adjacent. Tangent? Yeah, the tangent is the opposite over the adjacent, or if you like, the sine over the cosine. Okay, so let's set up that equation. So the tangent of 25.7 degrees is equal to what? Something.
X over 532.
X over 532. Okay. So if I solve for x, x is just 532 times the tangent of 25.7 degrees. Okay. I want some brave individual to take their calculator, maybe multiple. Make sure you are in degree mode. Now, who here knows how to set degree mode? Anyone know how to set? Okay. Henry, this is a little weird. Because people are going to do it, I want them to see what happens. Please set yours to radian mode. But solve the problem anyway.
I didn't even.
Oh, you didn't bring it. Oh, you know how, but you can. Someone know how who has a calculator? Okay, you know how to set? You're our control here. You're going to show us how to do it wrong. Somebody else, multiply 532 times the tangent of 25.7. And tell me what you get. Yes?
256.
256. Okay.
That's in degree mode, but radians is different.
No, I wanted the right answer from Jada.
Okay.
Kayla's is gonna show us what happens when you do this wrong.
That's 25.7.
Yeah.
That's it.
Yeah. You did 338.94.
All right, that's good enough. All right. This is unfortunate because both of these actually look plausible, right? One of them is wrong. It would be nice if you had something like negative 0.6 or something that you go, no, that's not right. So in a way, it's good. You realize you have to check. You have to check to make sure you're in the right mode, that you're going to be entering your angle. Okay, thank you for doing it the wrong way. All right. Okay. Any questions about the height of the tree?
Why is it a different answer for degree or radians?
Let me answer it this way. Let's say I give you a meter stick, right? And I say, I want you to measure from here to here, right? and instead of telling me the answer in meters, you tell me in feet. It's not right, is it? It's the same thing. We're using the wrong scale. I mean, if you converted 25.7 to radians and then used radian mode, it would work. How would we convert 27? Kayla, hang in there. You still have it in radian mode? Okay. How would I convert 25.7 to radians? What would I multiply that by? Yes?
Would it be like 180 or 260?
180.
Oh, I was asking if it was 180 or 360. So like one of those.
180 over 2 pi.
Okay, let's not be confused. Easy to confuse.
Over pi. Oh,
360 degrees, that's a circle, equals 2 pi. So 180 equals pi. So it's going to be pi. Okay, would you multiply 25.7 times 180 divided by pi? Just approximately, what do you get? $1,472.5.
472.5.
Yeah, that doesn't sound right, does it? What did we do wrong? Oh, wait a minute. This is degrees and this is degrees. To multiply degrees by degrees, I get degrees squared. That's not what I want, right? I want radians.
Radians has to do with
Maybe this is what I want. I mean, I'm going through this because I know, I could come up here and try and do everything exactly right, and you'd never think it's possible. But you can make a mistake like that. You want to be able to see it. Yes?
It's 0.449.
Okay, we'll just say 0.449. Okay, so that's radians. And now I can indulge you one last time. Would you multiply 532 times the tangent of 0.449 in radian mode?
$256.
All right, isn't that nice? That's what we would hope. Right. Okay. Going to go on a little bit today. Fortunately, right now I need the computer again. Slight miscalculation. So we're going to start looking now at the graphs of trigonometric functions. We'll start with So this is a graph of the sine function, sometimes called a sine curve. Does anyone run into one of these curves in everyday life, they recall? Okay, I know immediately there are no electrical engineers here. Because any electrical engineer would at some point turn on their oscilloscope. And oscilloscope is kind of like a TV set. It's got a trace that kind of moves at some speed across it. You can control it. And then up and down, you let it be controlled by some voltage. So you plug it into the wall, and you adjust everything, and you see that the electricity in the wall is going up and down 60 times a second, 60 hertz. Yes?
I was going to say robotics, we don't sell that.
Okay. So why didn't you raise your hand when I asked if you... All right. You're just shy, that's all, Alex. Sorry. Okay. So that's I'm graphing here the sine of, we'll just say the sine of x for now. We'll call that the x-axis. And we want to know a little bit more about manipulating a sine curve, what we can do to it. Basically, this is what we were doing when we were doing translations and shifts and dilations. So we're just going to go right at it, the whole thing at once. What we want to know is, when we're graphing a function, a times the sine of some constant b times x minus some c plus some d. We want to know what a, b, c, and d do to this graph. So we're going to take a look. First thing I'm going to do, I'm going to try putting an a on there. Okay, so that's the sine. Let's do a different one. 2 sine. What do we see? This is just a dilation where we've multiplied the height. The height here is what we call the amplitude. Actually, the amplitude is not the entire height, it's just half the height. And our coefficient here, in this case 2, you can see is the amplitude. If I make it 3, it's going to be 3. If I make it half, it's going to be half. So that's what the A does. Conveniently, A is the amplitude. Okay. Let's hold our amplitude fixed, and let's just add a d value. Actually, oh, okay. What happened there? Well, this is just a shift, right? We've seen that before. We add a value to the function, raises it, I subtract some value, just going to lower it. 9, that's better. So the d is just a horizontal shift. And if I might add, it's shifting it in the obvious direction. You add a value, it moves up. You subtract a value, it moves down. Okay. let's look at what the C value does. Just move it a little bit. Okay. So now I'm subtracting the C value, but what direction did it move in?
To the right.
Moves to the right. Just like we learned for a general function, right? It's counterintuitive. Right? If you subtract a value, it moves to the right. If I add a value, it's going to move to the left. Okay. That's clear enough. So C value is nobody. I expect you to notice when I'm brain dead up here. This is vertical, right? Horizontal. I'm pretty sure that my right hand is ruled by the non-math portion of my brain. So when I'm talking and I tell it to go do something, it doesn't know what it's doing. All right, horizontal shift, but I'm just going to say reverse here because I want you to remember it's not the direction you'd expect. All right, finally we have this B value. What does the B value do? So I'm gonna put 2 here. What do you think is gonna happen? Yes.
Compress or stretch.
I like the way you said that. You said compress or stretch it. You see that? See, you have that problem too. Your hands don't know math, right? Right? They got it backwards, right? Right. Put it 2. Yeah, it compresses it. 6.
Bye.
If I put a number smaller than 1, it's of course going to expand.
Yeah, let me know.
Okay, so what is it expanding? What is contracting here? Well,
Yeah, if you need any more pictures or something, I think they're all shared.
depending upon the terminology we want to use, let's see, b greater than 0, the period contracts, b less than 0, the period, this is the period of a periodic function, right, expands. So you can see my cursor, right? So the period here, let's go back to 2 for a second. So the period on the pink line here, you can see, goes from 0 up, down, and then back to about 6 point something, 6.282 pi. But now, if I look at the green here, it goes from 0 up and down to about 3.14 pi. Right? Let's get a handle on that. So if b is 1, period is 2 pi. B is 2, period is pi. So what could I say about the period in general? Can we make a extrapolation here? I wanted to say, what's the period in terms of B? Anybody figure that out? that help? Does that help? What's the formula for the, yes?
2 pi over n.
Very good. We're calling n here b, right?
Oh, yeah.
Like the b value, yes. Okay. So that's the period. We also, I don't know if I mentioned this before, we have this term, it's called, so this is the period. That's the, you know, when you get into physics, that's your wavelength. Your wavelength. You also have, oh, and the period, what are the units on period? Well, it depends on what you're measuring, I guess. It's going to be, could be distance. Usually wavelength would be distance. We also are going to define frequency, which is 1 over the period. So therefore, it's just going to be b over 2 pi. And frequency has the inverse units, 1 over distance. Or that's not really what we use. That's not what we do with frequency. Frequency is time. This is distance for time. This is time for distance. Or frequency would be 50 cycles, 50 Hertz, 50 times a second. I hear that noise. It's I'm about to ready to the end of my class. All right, we'll stop here.